We're going to be going over purines, purine nucleotides, and we're going to start with Denovo synthesis. Then we're going to go ahead and hit salvage, so you've already made them and you want to recycle them. And then we're going to hit 2 diseases. Something to bear in mind is that through this there are a total of 5 particularly important enzymes that you'll want to know. 2 of them are in the pentose phosphate pathway in Denovo synthesis, and then the other 3 are salvage enzymes. Alright, so keep an eye out for those. Oh, and the diseases are when enzymes go wrong, which is why we really want to focus on those 5 enzymes. So, Denovo, making it from nothing, so it's completely new. It's being put together. Novo means new, from newness, whatever. Alright, I should learn Latin. So, pentose phosphate pathway, as we remember from back in Q1, pentose phosphate pathway is going to branch off of glycolysis. And one of the units in the pentose phosphate pathway, right after, when it starts splitting into 2 molecules, right after ribulose 5-phosphate, then it splits into xylose 5-phosphate and ribose 5-phosphate. Ribose 5-phosphate is what leads to purine synthesis. So I'm going to start with ribose 5-phosphate right here. Ribose 5-phosphate. All right, so ribose 5-phosphate is going to be acted on by PRPP, which is an enzyme, and this is synthetase. And it's going to take, as I recall, 2 ATP, and then it forms PRPP. And then PRPP is acted on by PRPP aminotransferase. Actually, it's amidotransferase. Amido, so amides are probably involved, if I had to guess. I haven't looked at the exact structure transfer, but... Alright, so these 2 enzymes then direct you towards forming IMP. Okay? So, IMP can be changed into either of the purines. It can either become ATP or GTP. Now, if you're going towards ATP, you're going to have aspartate, involved, and if you're going towards GTP, then you're going to have glutamine involved. And double check the aspartate. It's also possible that it's asparagine, but it starts with A. And these are the NH3, what's that called? Ammonia. These are the ammonia sources, as I understand it. And so that is how you form these 2. You go from ribose to PRP to IMP, and IMP becomes ATP and GTP. So you make the ribose sugar. You're taking the ribose sugar from the pentose phosphate pathway, and then you're adding the nitrogens from these guys, and then that makes your ATP or GTP. How can you remember which ones are... Go ahead.
Where does that synthetase come in?
Synthetase is acting to change ribose 5-phosphate into PRPP. Okay, so it's forming synthetase, it's forming PRPP, so it's called PRPP synthetase.
Gotcha.
And then PRPP is being acted on by PRPP amidotransferase. And it's also called, named based on how it's functioning. And so, I think that that's how much you need to know from this. Technically, right here, you also have fumarate coming off as a byproduct in the ATP. And it's possible there might be one question on something like that. All right. So focus on the 2 enzymes and then the 2 origins for each of these nucleotides. And so if you have those, if you know the enzymes, then their names tell you what the molecules around them are. So there's just PRPP synthetase, PRPP amidotransferase. That tells you everything starting from the pentose phosphate pathway. So you do need to know ribose 5-phosphate is what it's created from. Okay?
Okay.
All right. So with this said, I probably should have flipped these a little bit. Purines.
No, it is aspartate.
It is aspartate. Thank you.
Just looked it up.
We've now verified, due to Derek's vigilance, that it is aspartate.
This just in.
This just in. All right. So over here, I'm going to go ahead and do our second topic now. Actually, really quick, if you want to review at home, go ahead and pause and review the 2 enzymes, the 2 precursors, and then what they make. And actually, before we move on, there is one mnemonic that you might find helpful. If you can do this without it, fine. But some of you might be familiar with all girls are pure. All stands for ATP or adenosine. Girl stands for GTP or guanosine. Are pure. Pure stands for purine. All girls are pure. And you can also add the I. Ideally, all girls are pure. Anyway. And I modified it a bit so that it can be the sentence, ideally, all girls are pure. And then you just have a double repeat, and you remember that aspartate and goes with ATP, and glutamine goes with GTP because they start with the same letter. So if you like wordplay, then maybe that works for you. If that sounds like a knot of tangled string and you're wondering why I brought it up, erase it from your mind. All right, moving on to pieces of a purine. All right, so purines have 2 rings, and I'm not even going to promise to have the right number of sides to these rings. So chemists out there, Yakira, go ahead and ignore anything that's wrong and exactly how many. But I do know that the backbone of the ring, so these 3 carbons are coming from glycine is the backbone of that. And then you also have glutamine and aspartate. Okay, so we have glycine, glutamine, and aspartate, donating carbons. And those are the 3 amino acids. You also have, Derek, if you can be our news reporter and look up the exact name of N10 formal methylate or something like that. Formal TH, yeah, it's like N10 methyl formal thief is how I remembered it, because it was like THF.
Yep, N10 formal THF.
N10 formal THF. THF.
Formal FORMYL.
YL. Alright, formula thief. Alright, and this donates a couple carbons, and I think it's that one, and then aspartate does like the, no, and it's actually, it doesn't matter which one, I'm being anal at the moment. It's that one and that one. Alright, I think. Anyway, it doesn't matter which carbons are donated, just know that carbons come from glycine, glutamine, and aspartate, as well as N10 formal thief, is how I remember it, and I just have a thief in a tuxedo. And then glutamine, you know that there are 2 nitrogen groups in glutamine, so you know that it's going to be donating how many? 2, right? Pretty sure that's, and we can verify. This is, I'm a little bit, so.
Yeah, that's what I understand too.
Okay, great.
And actually,
I need backup today, because.
Yep, this glutamine has 2 nitrogens. Any other questions?
It's if it donates both of them, and I'm pretty sure it does because it's integrated. Thank you. All right, so I'm not able to verify mentally at the moment. All right, so those are the 3. There's one, there's one, there's one, and then you also get carbon from this. Okay, so if you want to at home, you can go ahead and pause and then review the first thing with the 2 enzymes, the 2 products, and then the 4 origins of what makes the actual structure of the rings. We're obviously skipping some steps in here. If we knew every single step of de novo synthesis, we'd see where every one of these comes in. And so, great, we're going to go ahead and move on. Something that I have a question about, and if you guys know, it would be great, is right here, we see that aspartate is used. Right here, we see glutamine is used, and they were put in the pathway only on one side of these GTP, ATP, and yet over here we see that aspartate and glutamine are part of the structure of like the basic double ring. And so are we just using another one? So that's something that I don't know, and I haven't had time to verify. I know that this is...
Where does that fit in? Where is that structure that you drew? Is that IMP, or is that...
This is probably IMP. This is the double ring, the basic double ring, before it's made into ATP or GTP, so I believe it's IMP. I haven't verified that.
Okay.
I know that every single purine has this skeleton, and IMP is supposed to be the skeleton, but I haven't actually gone and found the name for this skeleton. I'm assuming it's IMP.
Yeah, it doesn't say on the slides, so I don't know.
Okay.
But yeah, I guess we can just Google it,
Yeah.
Look up in the
professionally verify it.
Yes,
okay.
That's what I meant.
All right. That's what you did say. Man, these people, they need to get their hearing.
What? You mean
out.
Google isn't a professional way of verifying?
Shh. All right, we're having technical difficulties. We have sound files coming in from another room. All right. All right. So hopefully that was helpful.
Oh.
Gonna go ahead and. You got a thing?
It has the chemical structure of IMP on slide 17 for those watching at home. Let me toggle between these two slides. So
here, let's just hold it up in front of the thing for them.
Oh, they'll see my notes.
They would love to see your notes.
Oh, can you see it?
So
it's right there on the bottom. Center. You have IMP, and I'm going to go up to where. So you see there are some differences between the two, and I'm not a good memorizer, so let's go back. Oh no, where is it? Okay, I'm totally losing it now. Okay, so there's that one, and then there's this one.
And you can also see on that slide the PRPP being acted on.
So there's a carboxyl group that's different.
Okay, so it's almost the same. So it's probably right before, and as we know, we skip a lot of the tiny steps in biochem. So there's probably a few intermediate steps before the IMP, and then the IMP has that going on, if I had to guess. Anyway, gonna go ahead and erase this stuff and move to salvage. All right, salvage. Gonna make this bigger. So we have ATP, and then we have IMP, and this is basically the slide, honestly. And then we have GTP, and we have an enzyme out here. You guys will probably remember this slide. An enzyme out here. And then we have adenosine. Oh, no. Yes, it's adenosine. And then, no, it's adenine. Adenine. All right. Adenine. All right. And then right here we have adenosine. Now, with the S there, ribose, the sugar, has the letter S in it, ribose. So you can remember that the difference between adenosine and adenine is that there's an S, and this one has a ribose. Adenosine still has the ribose attached. And then right here there's an enzyme that we don't need to know that takes the ribose off, so adenine. Anyway, so Here we have xanthine, if I remember right, and then it's homoxanthine definitely down here. And actually, I'm going to go ahead and say, I think xanthine was actually, and this one right here that I'm writing right now wasn't on the slide, but it is what homoxanthine and adenine can be turned into, and then that goes to uric acid. All right, so, and then there's an intermediate that she never mentioned us needing to know, and so it's just without the regular sugar. And then over here we have guanine and guanosine. So guanosine, guanine. All right, so this is basically the slide. What you need to know is ATP gets broken down and used up and eventually ends up being adenine, and then to make it usable again, you use APRT is the enzyme name, adenine phosphoribotransferase, something like that. It's so phosphate and ribose, and that recycles it back to ATP. And so you have this cycle going on the entire time. The second enzyme is H for homoxanthine, G for guanine, PRT, phosphoribotransferase. Okay, and so this is just recycling. It goes down and then it goes up. This one, same thing. This one just happens to work for both. So it goes to there, and then this gets recycled up. Okay, so we have APERT and HIGPERT. HIGPERT sounds like a weird name. All right. And if you don't recycle them, then they will go down to xanthine via xanthine oxidase. Which technically isn't an enzyme that she specifically said we needed to know, so that would be our secret sixth enzyme if you like knowing this kind of stuff. And xanthine oxidase acts both on homoxanthine and xanthine to keep degrading them down to uric acid. Okay?
Why is guanosine out there by itself?
Because GTP breaks down to guanosine, breaks down to guanine, and I was lazy. So.
And then xanthine oxidase is?
It breaks homoxanthine down to xanthine and xanthine down to uric acid. It gets used twice.
Xanthine oxidase.
So it's acting on that guy and that guy.
With the homoxanthine and the adenosine? Adenine?
It may be a different enzyme that breaks adenine down to xanthine. It may be the same enzyme. I didn't capture that. She doesn't expect us to know it.
Okay.
But definitely xanthine oxidase works on things with xanthine in their name, and it might work on adenine. And I'm glad that I finally remembered how to pronounce adenine in this video because I was having problems. All right.
Okay.
All right, and then last enzyme that we need to know out of the 5 main ones and our little bonus one down there is ADA. ADA allows you to change, and by the way, this is a double arrow for conceptual things. I'll explain that in just a second. Adenosine you can make into this other intermediate that'll make so that you can change it into IMP, and so that puts it into this cycle. See what I'm saying? And then that means that IMP, you can now shift it to make GTP, because in our last thing that we were talking about, you notice that IMP could become ATP or GTP. Well, what if you have enough ATP and you want to make more GTP? ADA. ADA allows you to shift away from adenosine into the IMP, and then you can shift it to GTP. And if you don't have ADA functioning, then you can get a buildup of adenosine. And so this is the third enzyme of the salvage pathway that you need to know. And this is the bonus one down here. She might ask on that, but when talking with her, she said that the 5 major ones are the 2 in PPP, and then these 3 in salvage. I think that xanthine oxidase is worth knowing because it has to do directly with the creation of uric acid. which is, it leads to gout, and it can lead to kidney stones, and it can be, so. All right, 2 diseases.
What does ADA turn into?
ADA, that's the enzyme.
Or what is it?
I don't remember the name. You probably got it right there if you want to pull it.
I don't know where it is, though.
Americans with Disabilities Act.
It turns it into something. Yeah, sorry, today's not a day.
Here's the photo, but I don't see the.
There was another one besides that one. That slide doesn't have it. There's another slide that has it.
Oh, another slide set?
Yep, and she didn't seem to care about that particular thing. The idea was that it was shifting it into this other cycle. That's what she wanted us to know. She didn't want us to know, like, that specifically. It's good to know, but it's not something that I'd be super stressed about. So pick it up if you want. If you want to.
Do you know what ADA stands for, or do you think we need to memorize that?
ADA is a vitamin, I think. I used to know. I don't know today. Should we know what ADA stands for? For general intelligence, yes. For the test, I'm pretty sure that she will have it in ADA form from the way that she was treating it. And I didn't ask her that specifically, but she really didn't seem. My read on it was that it was good as ADA.
Okay.
All right. So that's salvage. For those of you who want to at home, you can pause, go over the first 2, which are pretty fast, and then go over this one. Or, whatever floats your boat. Review helps for a lot of people.
Just a second. So what is this actually doing?
What is this doing?
So it's taking ATP and what's IMP?
IMP is a precursor to ATP and GTP. Why it gets broken down exactly like this? Great question. Maybe it obviously gets used for some processes that we haven't looked at yet. Otherwise, why would it be broken down? But ATP and GTP make really good sense. So I'll use them as the examples because we're familiar with them. IMP is probably the same thing. All right, GTP, you use it and you break it down to GDP, GMP, and then maybe even just straight up guanosine. Once you get to guanosine, it's going to be broken down to guanine, and then, we need more GTP again. So we go ahead and stick phosphates on this using this, and a ribose back on it because that came off, so that it is GTP again.
Okay, the HGPRT.
Yes, Higpert.
Okay.
Yep.
So the salvage pathways are basically those 2 blobs, or putting it back. Enzymes, or putting it back on. Okay, and then the rest is shown as just the catabolism of.
Yep, down here is catabolism, up here is recycling and salvage.
Okay, so Denovo is making it from scratch. This one's making it from the breakdown.
Yep, from scratch, recycling. What can go wrong is what we're going to move into.
Okay, that makes sense now.
Great. And by the way, this little double arrow right here is worth just noticing. I doubt that there will be a test question on it this time, but when boards come, it'll be like, I know that. So adenine can actually, without using this enzyme over here, become adenosine, and then that allows ADA to shift it without it having to become ATP first, and then be broken down from ATP. Whereas some of these other ones don't have a double-sided arrow, but adenine can go back up to adenosine. It's a reversible reaction right here with the ribose sugar being put on and off. And that's just interesting to know. It's not something you need to memorize. It's just like, conceptually, sometime in the future, a year in the future, when you're starting to kind of look at boards and probably more diseases in depth, that might be something that's good to just wrap your head around. Concepts is really more of what it is. And so that you're more familiar with, why is that thing going to be double? Why would we have an enzyme going both ways? There's going to be a reason. And so the more that you recognize, like, I see why they did that, the easier it is to start memorizing, learning, and understanding faster all the new things. And so that's just a cool little...
Okay, and ATP, that could be AMP?
Yeah, ATP probably breaks down to ADP, AMP, and then just adenosine. Once all the phosphates are gone, then you take the ribose off and you only have the base left.
Okay.
Because something that we know when they're broken down, and this is, I don't want to step in, we're in purines right now, so I'm going to stay in purines, but phosphate comes off first when you're just doing degradation. And I'm pretty sure this is true for all nucleotides, definitely for pyrimidines. Definitely for pyrimidines, but I'm pretty sure it's also for purines, but I haven't verified it. Phosphate comes off first, then the sugar comes off and is used, and then you have the base left that makes the products. These are bases, all of these, and they get made into uric acid, and guanine eventually gets made into uric acid. I don't remember the exact degradation. It probably gets changed into xanthine, and then xanthine oxidase acts on it. Does it show on there? If you can verify that guanine goes to xanthine, I'm almost positive.
Yes, it does.
It should. I don't remember memorizing that, but it's the only thing that makes logical sense. Thank you. All right, so phosphate comes off, then sugar, and then the base is what you break down to make all those interesting products that we're trying to know. Everything else, obviously, is a phosphate. I mean, you're going to use it like a phosphate. And sugar, you're going to use it for energy or maybe sticking it on something. So once you have the base left, you're either going to recycle the base or break it down. So, cool. Any? No. This is great. This is much more enjoyable to me, is going into nitpicky details.
So why do you think they have this whole pathway? Like we have ATP. Why don't we just use ATP instead of break it down to adenine? And it's like, let's make ATP again. Like, what's the purpose behind all that? So
we're going into what makes logical sense, but I haven't researched. Here's my idea. Here's what makes sense to me, and I'm like 90% sure that this is what's got to be happening in there. Obviously, ATP is an energy storage molecule most of the time. And so it's going to be used up. It probably goes ADP, AMP, and then there are going to be some enzymic processes that are just going to use that last phosphate and just make it adenosine. And so you're actually fueling some bodily processes with AMP. It's just not as common. And they're lower energy processes, which also might explain why we don't talk about them as much, because they're probably doing smaller things that aren't as, we'll just stick with saying that they're going to be lower energy processes. And I won't even swear to that. Actually, would the last phosphate be easier or harder to break off? Regardless, some processes are going to use AMP, whether it's higher or lower energy. And so once you break off that last phosphate, you only have adenosine left. That's what adenosine is. There's no more phosphate. There's a ribose and a base.
Okay.
And so it goes ATP, ADP, AMP, adenosine. And there's just some enzymes and there's some reactions that are fueled by AMP. We just haven't talked about them.
Okay.
Cool?
Okay. Yeah.
And then once you have adenosine, it's like, can't go back up this way, so we go this way.
You could get all depleted and you can run out of...
Why don't we go back up this
phosphates.
Way? Oh, yeah.
Yeah, so you said probably you get all depleted, and then it's like body has to do something, so you has to make it somehow.
And you know what? It could be that this is guesswork at this point, but it could be that the AMP taking the last phosphate off is actually high energy, and I know I was hypothesizing it was low earlier, but it could be high energy, and if it is high energy, that makes it really hard to reverse it, but really easy to break it off. And then that would mean that it would be really hard to reverse it right there, because all the reactions that are using it aren't going to want to go backwards. And so you go from something else, and we already have, this is a slightly different enzyme than PRPP, but since we already have the base made, we would recycle the base, and we'd do it through an indirect recycling, because a direct recycling would mean that you're putting in it's not a favorable reaction. If it's going to be a high energy bond that you broke, then you want to go around that, because it would be really hard to make so that you actually could make it efficiently, because it would be a really slow reaction.
You need an extreme science warning when you go off on these tangents.
It's so much fun! Helps solidify to me what's really happening. even though
Mm-hmm.
I don't understand it. Now I'm like, okay, now I can kind of know what this process is doing, but okay.
The more you poke at it, the more all the other stuff starts to make sense. And once you can get guesswork that's pretty decent. Anyway, it's fun.
Okay.
We'll just leave it at that.
Anyways,
it's fun.
you can erase it now.
Okay. Are
Thank
you sure?
Thank you for answering my questions and solidifying.
No, this is that's what I love doing that. I love going into. I actually. Well, I spent like 2 hours thinking about what would happen if you froze time. And if you froze time and only you could move, no air molecules could move unless you physically move them, you know, like in those movies, magic happens or super science or whatever. And it's like, as soon as you move, if the air molecules can't move, you're creating a vacuum wherever your arm just moved from. Would that vacuum cause so that since there are no longer molecules bouncing on your arm, which is keeping so that your atoms are in place, because part of what keeps everything where it is bond energy. The other part is because other things are always pushing on it to keep it there, and that's why being a vacuum in space can have such bad things. It's not a pure vacuum. A pure vacuum might be so bad that you literally would like start disintegrating, and I'm like, oh, would that happen because there's no longer molecules bouncing to keep you in place? Anyway.
Science geek.
Oh, it's fun. It's great.
You can make a pure vacuum though.
You can.
Guys.
Okay, what's
Study.
Two diseases.
Test.
2 diseases. 1, science nerd. 2, dork. Okay. 2 diseases. 1 is called Lesh-Nai-Han. Lesh-Nai-Han. All right, sounds sort of Chinese to me. And so if you guys are familiar with Bill Nye the Science Guy, Bill Nye the Science Guy, Bill. Okay, if you've seen it, that would bring back the memory. I just remember him, except he's in a Chinese, he's dressed Chinese. And so Leshe, and he's holding a leash. This one, regardless of how you remember it, is the one that has the enzyme HGPRT not working, which means that we can't recycle GTP, which we had over here, GTP, or IMP. And so if you can't recycle those, then where are they going to go? Down to xanthine. And from xanthine to uric acid. Even I can't read that. Okay. Okay. So if this is broken, that's called Lesh-Nai-Han. You're going to have a lot more uric acid because you don't have GTP or IMP. Cool? Cool. All right, next. Ginger.
What?
The next disease.
Von Gerke.
Bam. Just like you said earlier. All right. Yerke. All right. Von Gerke. If any of you are Black Cauldron fans, it's a book and a really old movie. And if you've seen the really old movie, which some people have mixed feelings about, but there's a creature called Gurgi. Gurgi, my little Gurgi. Yeah, and that's how he talks. And I always remember that this is affecting an enzyme. If you look at glycolysis and gluconeogenesis, and there's 10 steps, about here is where you have glucose, like basically the top. You have glucose 6-phosphatase, which is making so that it's in gluconeogenesis to make glucose to push it out into the bloodstream. Okay? Phosphatase. Phosphatase. And this is gluconeogenesis, and in the liver you have this one, and that's what makes free glucose. After you've done all of it, and then the last step, only the liver can do it to put it out into the bloodstream. This is what is broken in von Gerke. And you have to do a funny thing in your throat to sound like Gurgi and Black Cauldron. If you like Black Cauldron, this is probably lost on like everybody watching. But this reminds me, like, throat is high up. I probably shouldn't have shared this one, but it's so fun to sound like Gurgi. Gurgi! All right. So, anyway, if this enzyme is broken, then you're going to be shifted to the PPP pathway, the pentose phosphate pathway. If you're shifted to the pentose phosphate pathway, then you have a heck of a lot of all the intermediates of that, including ribose 5-phosphate. If you have a lot of ribose 5-phosphate, that's a positive regulator for, it's a reactant for the reaction of forming PRPP. And PRPP eventually makes IMP, makes GTP, makes ATP. And so if you have a lot of that product, which is going to happen if you're in the pentose phosphate pathway more than you normally would be, then you're going to make that reaction happen more. It's not that the yeah, we'll leave it there. So,
so since the G6P phosphatase is defective, it'll go to the PPP pathway and make ribose 5-phosphate, which will
then be acted on by PRPP synthetase, which we just talked about over there as one of the first two enzymes, and PRPP amidotransferase, which we also talked about, and then you're going to have, basically it's causing a buildup of G6P. That's the enzyme, but you have a whole bunch of G6P, which means, and G6P is a reactant, and if you have a whole bunch of reactants, then it forces a reaction to happen. Or if you want to think of it as positive regulation, you can do that too.
Okay, so it
forces pentose phosphate pathway.
So this is a
which forces ribose 5-phosphate, which forces PRPP, which forces IMP, etc. to uric acid. Because here's when this would be happening, by the way, and this could be a question. So in gluconeogenesis, oh, we're low on glucose, we need to make new stuff. We're going to be trying to go this way, because all of those enzymes will have positive regulation because we need glucose. So like that one and that one, and then all the ones in the middle will have reverse. They'll be going towards glucose, okay? Because gluconeogenesis, just because you need glucose. Well, if you can't do the last step, that doesn't turn off all the other enzymes. They're still going to be making the stuff. So you're going to have a huge buildup of the thing that this broken enzyme is supposed to make into glucose. As soon as you get a huge buildup of it, it's going to run into the pentose phosphate enzyme somewhere in the cytosol, even though the cell is like, oh, that's not what I'm trying to do. And so then that enzyme is going to act on it, because whenever it touches G6P, it's going to do its thing. And if there's a frickin' ton of G6P throughout the entire cytosol of the cell, it's just going to happen. They're going to run into each other. And once this starts, it's irreversible. As soon as you get the pentose phosphate pathway started, there are irreversible reactions that happen, which means that as soon as it's changed into those intermediates, one of which is 6-phosphogluconate, you can't go backwards, and so you're going to make all this other stuff. And it'll probably try to shift some of it away from ribose 5-phosphate into the thing that puts it back into glycolysis, but what does that do? Because if you remember in the pentose phosphate pathway, you have two end results that are major. One is ribose 5-phosphate, the other one is the glyceraldehyde 3-phosphate and the fructose 6-phosphate, which are both back in this pathway. Well, you're still going to, so when you put them back in, great, fine, good job, you didn't make ribose 5-phosphate as much, you still made some. You're still going to be in gluconeogenesis mode, probably. And so you just go back up there, and you make more G6P, and it's floating in the cytosol, and it hits this, and it goes down. So pretty soon, you're going to have a frickin' ton of ribose 5-phosphate. There's no other exit. And so that is why this enzyme being broken is equivalent to saying uric acid. Because it forces it down that pathway anytime that you're in gluconeogenesis mode.
That's interesting, because this enzyme is not a nucleic acid
enzyme. No, it's
enzyme,
a gluconeogenesis.
But we're talking about it as a disease of nucleic acids.
Yeah, and but it only leaves one exit. So as a clinician, what can you do to help this person besides, like fixing their enzyme through, that would be great if you can get, honestly, you'd have to do like gene therapy. But there's a few things that you could do, but what would one lifestyle thing be that you could do to mitigate how much uric acid is made?
Always be in the fed state.
Bam. Always. I'm not saying this would be what you would actually recommend, because there might be other things going on. Always being in the fed state's like, you're taking in a lot of calories, dude, which causes another issue. But if you were just enough in the fed state, maybe, if you were making so that glycolysis was happening, you're not going to be trying to make glucose. So you're not going to have the buildup. And so you don't have the uric acid. So if uric acid is more of an issue to them than always being in the fed state, maybe they're anorexic too. Great. Solves both problems.
if you eat a lot,
graze all day.
If you eat a lot of food, if you become obese basically, and you do bit of oxidation, that's kind of that would help the problem, but the body would still want to do
other things.
Gluconeogenesis will probably still be triggered by
Gluconeogenesis. Yes.
The starving or the unfed state.
Oh yeah. Anytime you're in fasting and starvation,
so beta oxidation won't help this.
Beta oxidation, not directly. No, you'd be making.
So basically, with this patient, you say just small, frequent meals throughout the day.
Yeah.
Maybe even wake up and take a
midnight one. If the uric acid is that big a deal, yeah. But you could at least mitigate it by telling them to snack throughout the day, and you learn that by just like having fun with the biochemistry and like, ooh, what happens where? Why? Why does this disease do what it does? If that enzyme's broken, why doesn't it just go back down? Well, what state are they going to be in? Yeah. Okay. So that's everything. Leishman breaks Higpert, von Gerke breaks PPP, and anything else before I cut the video?
HGPPT. How do you memorize that? What's so the Leash, Nyman, Bill Nye.
HGPRT.
PRT? Oh, I just didn't. I always write super fast. It's supposed to be PRT.
PRT.
So here's how I memorize these. I know what they're doing, first of all. Phosphate, ribose, transferase. They're putting a phosphate back on. They're putting a ribose back on. We know that they're taking bases and making them into nucleotides. 3 parts of nucleotides: phosphate, ribose, and the base. Yeah. And so we have the base. It needs the other 2 things. So PRT, you can remember like that. And then HG, honestly, it sounds like a name to me. Higbert, except I say it with a P, Higpert. It sounds like one of those, my name's Higpert, you know. And so that's how I memorized that one. And then once I had this one, I just remembered the other one was for adenosine or adenine. And so then it's just APERT. PERT is also a word, P-E-R-T. You're kind of a PERT one, aren't you? It was used several decades ago. There's a bunch of little things you can do. How I did it was, the one that I chose was Higpert and then APERT. And it's just easy to say. Oh, that's Higpert, that's APERT. And once it's easy to say, it's easy to remember.
Okay.
And the letters right here, this stands for homoxanthine, which is why I remember that one. And this one stands for guanine. So it's homoxanthine guanine phosphoribotransferase. And so it's just naming what it does. It just happens to have a lot of letters in it. And so, and then APERT's the same thing. As for Leishman, I mentioned Bill Nye the Science Guy. And by the way, just for fun, if you need some stress relief, go watch some old Bill Nye stuff, because it was so cool. He was such a proud nerd. All right, so it was a kids' science TV show, but it never gets old. So cool. All right. Anything else before we go? Oh, it's gone.
Thank you very much.
All right. Thanks, guys. Best of luck. Go slay the finals.